Bismillah, Alhamdulillah, Assalatu Wassalamu ala Rasulillah, Sallallahu Alaihi Wasallam, wa ala alihi wa ashabihi ajmain. Allahumma salli wa sallim ala Nabiyyana Muhammad, Sallallahu Alaihi Wasallam. Assalamu alaikum. I'd like to welcome all of you in this presentation. Title of this presentation is Informed Design Process to Address CEP and CEA. CEP stands for Complex Engineering Problem Solving, and CEA stands for Complex Engineering Activities. In this presentation, we'll focus on these two important things, and we'll try to relate these two important things, CEP and CEA, with Informed Design Process, IDP. Let us use this acronym for Informed Design Process. Now, start with Informed Design Process. This is a process where there are 8 stages which are related to a design cycle. Related to a design cycle. So first, in the beginning of a design process, you should clarify problem specifications and constraints. Clarify problem specifications and constraints. Then you try to conduct research and investigate different things related to the project. This is more like literature review, typically known as literature review. So you need to do that. That's the second stage. Third stage is to generate alternative designs. So in the beginning, you generate alternative designs, then you choose and justify the optimal solution. So from these, you can have multiple alternative designs, 3, 4, 5. From those alternative designs, you select the best one. And you, of course, you'll have to justify that one, based on certain criteria. Then after you finalize your design, you have selected the optimized design, you go to the manufacturing phase. You develop a prototype. Then you need to assess the performance of the prototype. To do that, you'll have to test and evaluate. And you'll have to redesign the solution if needed. And usually it's needed. Sometimes you might change things here and there. So that's redesign the solution. And finally, once you are done, you have finalized your design, you need to communicate your achievements. And you need to tell others what you have done. So you need to do reporting, presentation, and project show, all these things. So that's the last step, communicate your achievements. So this is the informed design process. Now, what we are, required to do nowadays, especially for design courses, is to teach all the students how to solve complex engineering problems, and also engage in complex engineering activities. This is what we'll have to do. But from where we are getting this? Why we'll have to do this? What's the reason? What's the justification? What's the rationale? What's the big deal, so to say? What's the big deal to do all this stuff? The reason is nowadays for engineering education is something called the Washington Accord. What is this Washington Accord? This is an international agreement between bodies responsible for accrediting engineering degree programs. Now, there are right now 21 countries who are full signatories. We have countries like Australia, Canada, China, Taipei, Costa Rica, Hong Kong, India. India became a member in the year 2014. Ireland, Japan, Korea, Malaysia. Malaysia became a member in the year 2009. New Zealand, Pakistan, even Pakistan became a member in the year 2017. Peru, Russia, Singapore, South Africa, Sri Lanka, even this one of our neighboring countries, Sri Lanka became a member in the same year like India in the year 2014. Then Turkey, US, the UK. So these are the 21 countries who are full signatories. What does it mean? I mean, they have this so-called mutual recognition. So if the accreditation agency in India, if they give accreditation to certain program, then those graduates, I mean, their degrees will be recognized by other signatories, other countries who have participated in this Washington Accord. So the Indian, suppose the Indian accreditation agency has accredited, let's say, IIT Kharagpur. So all the graduates of IIT Kharagpur will be recognized by Malaysia, Pakistan, Sri Lanka, Turkey, US, UK, like that. So unfortunately, our country is still, it's waiting. Right now, Bangladesh has provisional status. It's one of the provisional signatories. There are 7 countries right now with who are following under this, I mean, falling under this provisional signatory status, like Chile, Thailand, Bangladesh, Mexico, Philippines, Myanmar, Indonesia. Yeah. So we are hoping very soon Bangladesh, inshallah, will attain its full rights. When it, I mean, Bangladesh, the accreditation agency of Bangladesh will have the full right, then whichever program is accredited by that agency will be recognized by all these countries. Yeah, all these countries. That will be an excellent thing. Okay, now let us talk about OBE, outcome-based education. So outcome-based education is an educational theory that bases each part of an educational system on goals or outcomes. So we can also say that outcome-based education means clearly focusing and organizing everything in an educational system around what is essential for all the students. So this is very critical. What is essential for all students to be able to do successfully at the end of their learning experiences? So suppose in engineering programs, the goal is to prepare balanced graduates who will be able to survive in the market, able to do different useful things for the society. So the programs are, I mean, preparing all the graduates with certain goals or outcomes. Yeah, even for all whatever courses we are implementing in the engineering programs nowadays, those are all of them are based on certain outcomes. Yeah. Also, we can say that in OBE, the faculty of a program reaches consensus on a set of program learning outcomes, knowledge, skills, and attitudes that the students are supposed to acquire by the time they graduate. So in engineering program, we try to infuse different types of knowledge, different types of skills, and also different types of attitudes or behaviors among the graduates, yeah, among the students or learners. Yeah, these are 3 important things. You can use the acronym KSA, knowledge, skills, and attitude. Yeah, so you attain different types of knowledge, skills, and attitudes. Now, there are 12 graduate attributes which we are focusing here at OST. There are 12 graduate attributes. 5 of them are related to core engineering sides. They're related to analysis of problems and synthesis of solutions, like, and they are denoted by this PO1, PO2, PO3, PO4, PO5. PO1 is engineering knowledge. engineering knowledge. PO2, problem analysis. PO3 is related to design and development of solutions. So all the design related courses in mechanical engineering, they should have this PO3. Yeah, the one at 3-1 level. Yeah, the sessional of measurement and instrumentation, that should have this. This machine design course should have it. Final year project and thesis, that should have this PO3. So this is a must. Also, PO4 is investigation, and PO5 is modern tool usage. Modern tool usage. So all the students, they should, whenever possible, they should learn relevant or related modern tool usage. Yeah, this is very important for the graduates. There are 3 program outcomes or graduate attributes which are related to responsibilities. PO6 is the engineer and society. PO7 is environment and sustainability. PO8 is ethics. These are, you can say, related to professional due diligence. So when you are implementing a design project, you need to see, I mean, you cannot forget the society. We are living in the societies, right? So you'll have to do the design for the society. Yeah, it should benefit them. It should not harm them, right? It should not harm them. Also, we should take care of sustainability, environment and sustainability. So if you're developing a product, yeah, it should promote something called sustainable development. Sustainable development. So it should not hamper the rights of the future generations. It should have minimal impacts. It should have minimal impact. So at different stages of your design, you should try to promote sustainability. Sustainability. And there are 3 dimensions: social, environmental, and economic. All these 3 dimensions of sustainability should be considered. And also PO8 is ethics. Of course, this is a very important graduate attribute. Very important graduate attribute, ethics. And this is extremely critical. This is extremely critical, and it should be maintained as well. Yeah. PO9 is individual work and teamwork. PO10 is communication. PO11, project management and finance. And PO12 is lifelong learning. Yeah. Lifelong learning means the graduates will have the eagerness to learn. Eagerness to learn. Washington Accord also demands that the graduates, engineering graduates, they come up, they get acquainted with 4 types of knowledge profiles. What are these knowledge profiles? Okay. And these are denoted by these Ks. Yeah. K1, K2, K3, K4, K5, K6, K7, K8. 8 types of knowledges. So what are these things what Washington Accord is demanding? The first one, K1, is related to natural sciences, physics, chemistry, yeah, and the basic sciences. K2, mathematics. K2 is mathematics. K3, engineering fundamentals. Engineering fundamentals, like fluid mechanics, solid mechanics, in the case of mechanical engineering, the basic engineering courses, thermodynamics, heat transfer, those engineering fundamentals. Specialist knowledge, they're all in, let's say in mechanical engineering, there are some courses which will address this specialist knowledge, like renewable energy, refrigeration and air conditioning, yeah, power plant engineering. These are special knowledge. K5, engineering design, which is related to all the design courses, final year project. In all these cases, you need this engineering design knowledge. K6, engineering practice. Engineering practice. So here On the third column, you're seeing more description about that knowledge profile. Like K6 is knowledge of engineering practice, technology in the practice areas in the engineering discipline. K7 is comprehension, and K8 is research literature. It's related to literature review. K8. So these are the 8 types of knowledge. Basically, the knowledge profile has 8 categories, and our engineering graduates, they should have them. Yeah. So I would request all of you to remember these 8 knowledge profiles. We'll come back to this. Eight knowledge profiles later on, inshallah. Yeah. So you can see that, I mean, K5 is specifically related to engineering design. Now we talk about CEP, complex engineering problem solving, CEP. So before we move to complex engineering right away, I mean, we need to focus that there are 3 types of engineering problems. 3 types of engineering problems. The first type is well-defined engineering problems, well-defined. So in this problem, when this is so well-defined, you'll have just, in many cases, you might have only one solution. Then we have broadly defined engineering problems, which are a little bit flexible. You don't have straight cut one answer. There might be several answers. Yeah, it can be broadly defined. And then we have complex engineering problems. We have complexities. There are different parts, different sorts of complexities. Yeah. So complex engineering problems, they are really encountered in engineering practices, and all the engineering programs, they should prepare their students to solve complex engineering problems. And we have a very nice definition from Abbott about complex engineering problems. So basically, complex engineering problems include one or more of the following characteristics. So this is how Abbott is, accreditation agency from the US, Abbott. Yeah. So according to them, the complex engineering problems should have one or more of the following characteristics. What are these following characteristics? Involving wide-ranging or conflicting technical issues. Wide-ranging or conflicting technical issues, or having no obvious solution. No obvious solution. It's unlike these well-defined engineering problems. You don't have only one, I mean, obvious solution. You don't, I mean, it's difficult to, I mean, imagine what will be the correct solution. Addressing problems not encompassed by current standards and codes. So complex engineering problems can, I mean, usually you don't have a published standards or codes which can be used and you can just fabricate the product. It's not like that. Involving diverse groups of stakeholders, including many components, component parts, or sub-problems, or involving multiple disciplines, or having significant consequences in a range of contexts. So according to Abbott, a complex problem is something like this. So Washington Accord has defined 7 ranges of complex engineering problem solving. So they have here, this is a kind of descriptive, I mean, the way Abbott has defined, it's not yet, I mean, it's not kind of razor sharp, but Washington Accord what is saying that there are different 7 ranges in complex engineering problem solving. Like they are denoted by P's, P1, P2, P3, P4, P5, P6, P7. So what are these ranges? P1 is related to depth of knowledge required. P2, range of conflicting requirements. P3, depth of analysis required. P4, familiarity of issues. P5, extent of applicable codes. P6, extent of stakeholder involvement and conflicting requirements. and P7 is interdependence. There are 7 ranges, and then which problem is a complex problem? So complex engineering problem, here it's written, complex engineering problems have characteristic P1. So this is a must. For complex engineering problem, this is a must. This is a must. Should be there. Must. P1 should be there. So depth of knowledge should be required. It should not be superficial. And some or all of P2 to P7. So in order to have a problem to become a complex engineering problem, P1 should be there, and then maybe 2 to 3 from P2 to P7 should be there. Yeah. So they're saying some or all of P2 to P7. So you don't have to have all the 7 ranges. Yeah, if you have, then this is super duper complex problem. But usually you might have P1 is a must. You might have 2 to 3 from P2 to P7. Yeah. So when you are selecting your problem, you should make it complex in this fashion. You should identify the complexity in this fashion. Yeah. Then for each P, there should be certain things like P1, depth of knowledge required. This is a must. P1 is a must for all the complex problems, that it cannot be resolved without in-depth engineering knowledge at the level of 1 or more of K3, K4, K5, K6, K8, which allows a fundamentals-based first principles analytical approach. So this P1 is a must for complex engineering problems. It is related to these 5 knowledge profiles: K3, K4, K5, K6, or K8. So P2 is, it should have, involve wide-ranging or conflicting technical, engineering, and other issues. But as I was trying to say earlier, yeah. So there might be different issues, technical issues, engineering issues, or other issues, ethical issues in your design problem. Depth of analysis required, so have no obvious solution and require abstract thinking, originality, creativity in analysis to formulate suitable models. P4 is involve infrequently encountered issues. So it should not be a very common one. P5, extent of applicable codes. So the complex problem, this range is related to problems which are outside problems encompassed by standards and codes of practice for professional engineering. Yeah. So this is a big issue. P6 is related to extent of stakeholder involvement and conflicting requirements. So in complex problem in this range, according to this range, it will involve diverse groups of stakeholders with widely varying needs. So there, in your project, in your design project, there can be different types of stakeholders. Different types of stakeholders. P7 is related to interdependence. So our high-level problems including many component parts or sub-program problems. Okay, so these are the 7 ranges of complex engineering problem. Now we move to complex engineering activities, CEA, complex engineering activities. For complex engineering activities, we have 5 ranges, which are related to range of resources, which is A1, then level of interaction, A2, innovation, A3, consequences for society and environment, A4, familiarity, A5. So these are 5 ranges of complex engineering activities demanded by the Washington Accord. Okay, and in the slides we have some descriptions like W1. A1 is related to, they involve the use of diverse resources And for this purpose, resources include people, money, equipment, materials, information, and technologies. A2 is level of interactions. So these complex engineering activities, by the way, these are related to your graduate attribute number 10. All these complex engineering activities, they are related to PO10. What is PO10? Do you remember PO10? What is PO10?
Communication, sir.
Communication. Thank you very much. That graduate attribute, communication. So complex engineering activities are related to different types of communication. You'll have to remember that. Yeah. So A2 is level of interaction. A3 is innovation, involve creative use of engineering principles and research-based knowledge in novel ways. A4 have significant consequences in range of contexts characterized by difficulty of prediction and mitigation. And A5 is familiarity. So these are 5 ranges of complex engineering activities. Now, in our system, I mean, our program, or in any program which are trying to implement the requirements of the Washington Accord, they should report complex engineering problem solving and complex engineering activities. So at OST, we have developed templates for different courses, which should be used. Okay, last topic is IDP, Informed Design Process to address CEP, Complex Engineering Problem Solving and Complex Engineering Activities. This is the last topic. So again, once again, so there are 8 stages in the informed design process. Clarify problem specification and constraints. Number 2, research and investigate. Number 3, generate alternative designs. Number 4, choose and justify the optimal solution. Number 5, develop a prototype. Number 6, test and evaluate. And number 7 is redesign the solution. What is number 8? What's the last one? Which one is the last one?
Test and evaluate.
Last one is communicate your achievements. Reporting. That's your reporting. Yeah, communication. Okay. Now, different stages, like the first one, clarify problem specification and constraint. We need to relate to those 7 ranges of complex engineering problem solving. So describe the problem clearly and fully, noting constraints and specifications. These are related to P2 and P6. Constraints. Constraint means limits imposed upon the solution. Yeah. Specification means the performance requirements the solution must meet. So this level, this step, clarify problem specification and constraint, is related to P2 and P6. Number 2, research and investigate. It's related to gather information related to P2 to P7 as much as possible. Yeah, search for and discuss solutions that presently exist to solve these or similar problems. So identify problems, issues, and questions that relate to addressing the design challenge. These are related. So related to steps 1 and 3. Generate alternative designs. Brainstorm and try to find multiple solutions related to P3. Don't stop when you have one solution that might work. It's related to P1. Yeah. Continue by approaching the challenge in new ways. It's not only related to P4, also that's one of the ranges of complex engineering problem. Also A5. Describe the alternative solutions you develop. It's related to P1 and 5 ranges of complex engineering activities. Choose and justify the optimal solution. In this case, it's related to several ranges of complex engineering problem solving and 3 ranges of complex engineering activities. Yeah. So later on, inshallah, these slides will be shared with you. You will see that different levels of informed design process they are related to different ranges of CEP and CEA. So that's really a very nice model which we have selected. yeah, for design. And when you develop your prototype, it's related to manufacturing. It's related to manufacturing, obviously. Yeah. Test and evaluate is related to 3 ranges of complex engineering problems: P1, P3, P5, also related to A1 and A2. Yeah. So there are some useful resources which you might be able to use in the future, inshallah. You'll have to use some tools here in your project. In the design projects, you use different types of tools. SimScale is quite popular. It's online based simulation platform. It's freely available. You can approach that. And ANSYS Academic, anybody can download that. You can download that free of charge legally, and you can use that to conduct for mechanical engineering design. You need to do FEA, finite element analysis. So ANSYS Academic can be used. And I hope in the near future, IMechE will arrange a boot camp, a training sessions for you, inshallah. That will help all of you, inshallah. So with this, I would like to end my today's presentation.